Good evening everyone, I am P. Vishnu. Today we are going to see Gradientdescent in training neural networks. We'll start with introduction to Gradientdescent and updating weights and bias using Gradientdescent and its implementation in MATLAB. So we'll start with what a gradient is. Say when we take an input from one dimension, we find the slope by differentiating with respect to input variable. But when the input belongs to n dimension, we have to find the partial derivative with respect to each variable. Gradient is a vector containing all the partial derivative, and it's denoted with nabla. Gradient always points to the direction of the maximum, which is called steepest ascent, where it always points towards the increasing direction, where the function is in increasing direction. The main intention of using any optimization function is to find maximum or minimum. For one dimension, we'll find derivative with respect to x or input variable and equate it to 0. For n dimension, we'll do gradient equal to 0. Suppose we are at a random location in a function, then our aim is to move towards maximum or minimum. So the question is in which direction we should move and how much we should move in each step. The thing in most of the optimization problems is we have to reduce the error function. So we have to find the minimization of the given function. New position is equal to previous position plus the direction in which we have to move, and step size means how long we have to move in each step to reach the new position. So here we want to move towards minimum, but gradient, as we have discussed, always points to the direction of steepest ascent. So we take the negative of the gradient to have the descent direction, that is direction in which the function is decreasing. So the next position is equal to current position minus of gradient, which will give descent direction into step size. Step size can be found in two ways. Find the value of the step size at which new position function value, and we'll find the minimum value of it, or randomly take the step size values. Here I have taken a small ANN architecture in order to demonstrate updating weights and biases using gradient descent. I have taken one input layer, one hidden layer, and one output layer, where each consists of two neurons each and two biases. These are the weights with respect to input layer and hidden layer, and these are the weights between hidden layer and output layer. I have initialized input values and weight and bias values in order to demonstrate this. Wij represent weight between ith neuron in the input and jth neuron in the next layer. In ANN, we will have sigmoid activation function, which is 1 divided by 1 plus e raised to minus x. Input to the hidden layer is equal to summation of product of all input layer neurons with corresponding weight plus biases. And output to the hidden layer will be, we have to pass this input to the hidden layer to the sigmoid activation function. Same. And output, and this will become input to the next layer. Feed forward propagation. As we have seen, input to the hidden layer is equal to the input layer neuron with corresponding weight, and we have equated the values, we got this value. Same for this, and output of the hidden layer we got this value. Similarly, we can find weight. This completes our feed forward propagation. Back propagation. Coming to the back propagation, we'll find the error. Error is actual value minus predicted value. we will take the square in order to neglect the negative term. And why we have to take the mean is different datasets will have different size. So in order to maintain uniqueness, we will take the mean of the error target minus t1. We have taken two outputs, so t1 is the actual value of the output y1 layer, and y1 out is actual predicted value. Now we have to update weights and bias using gradient descent algorithm. For w5, what gradient descent tells is new position equal to old position minus step size into gradient of that position. For w5, new is equal to w5 old minus alpha. Alpha is step size we have taken as 0.5 into gradient at w5, that is d total by dou w5. Dou E total by dou W5 is equal to dou E total by dou Y1 out into dou Y1 out by dou Y1 in into dou Y1 in into dou W5. That is this value. In the same way, we have to update the weights of W6, W7 and W8. These complete. For updating y1, we have to use this equation. Dou E total by dou w1 is equal to dou E total by dou h1 out into dou h1 out by dou h1 in into dou h1 in by dou w1. Here again, dou E total by dou h1 out is equal to dou E1 by dou h1 out into dou E2 by dou h1 out is equal to this value. Again, dou E1 by dou H1 out is equal to dou E1 by dou Y1 out into dou Y1 out by dou Y1 in into dou Y1 in by dou Y1 out. We can find the derivative of the easy of these completes for backward propagation. This is the gradient descent implementation in MATLAB. Code for the implementation of gradient descent in MATLAB. These are the basic commands we use in the MATLAB. Here we have taken this function. Inline is a function used in order to substitute the values in place of x1 and x2. And we'll use this at the rate of this in order to substitute a list of values for x1 and x2. Gradient is a function used to find the gradient of the function at that point. Again, same we have to do inline and at the rate. Hessian will find the Hessian at the function. Again, we have to do inline. Here x naught, I have taken values from 1 to 1 and I have taken a maximum up to 4 iterations. Here the condition is norm of grade is greater than total and iteration less than maximum iteration, which says gradient should be positive. Suppose if input belongs to two dimension, gradient is we will have dou f by dou x1 and dou f by dou x2. Norm will give the uh, Euclidean distance from origin to the gradient, and it should be greater than total, that is 0, and iteration should be less than maximum iteration. In this loop we will update the each new position and by increasing the iterations, and at last we will print the optimal results. This is I have showed in the MATLAB. This is the optimal solution what we have got. If you want to see each step, each iteration, our values keep on updating. This is the code for ANN implementation in MATLAB. Here I have defined sigmoid function and derivative of the sigmoid function which will be used in the backpropagation. And I have taken two inputs and two outputs. And these are the well I have insulated like number of epochs, learning rate, input layer neurons, hidden layer neurons, output layer neurons. And I have randomly initialized weights and biases with the help of rand function in MATLAB. Same for weights and biases. After that, I have taken loop in that I have to do feed forward propagation. That is, as you have seen, input layer activation is product of input layer and hidden weights, and this is added with the bias term. This is posited to the sigmoid activation function. And output layer activation, same hidden layer output will become the input to the output layer activation, and rest is the same. For the back propagation, we have taken error means expected output minus predicted output. This is what we have discussed in the theory. Same I have written in the code. And at last we have to print the results. This is what the results that we have got after printing the values. Drawbacks. Too small step size will converge to minima very lately. On the other hand, big step size will have the chance to jump from minima. Rate of convergence is less compared to Newton's method. Chance to struck at local minima. Thank you.